All right, everyone, welcome to our talk. I hope you're all enjoying Unite 2017 so far. My name is Charles Sanglimsuwan, and I've been working in games for a long time now. But today, I'm speaking to you as a developer relations engineer here at Unity Technologies. As a member of our enterprise support team, I have the opportunity to meet with developers from all over, such as yourselves, and help make sure that your game is running fast on a wide range of platforms, from iPhones shipped 5 years ago to high-powered game consoles like the Xbox One X. Joining me on stage today is an old friend and my former teammate from the Microsoft Xbox team. Please welcome Kevin Cogger. So for the past few years, we've been working closely with the Xbox team to bring Unity to Microsoft's game platforms. It's a key partnership that's allowed us to optimize Unity running on Xbox and bring cutting-edge tech back to Unity Core. Now, for confidentiality reasons, we're actually not often allowed to talk about the internals of console platforms under NDAs, which is why we're really excited to be here today, because we're going to be doing just that. Our talk today is aptly titled Advanced Rendering in Unity, Dynamic Resolution, and HDR. We'll be focusing on two key rendering technologies that Unity developers can take advantage of to help bring their games to life and push the limits of the Xbox console hardware. Now, if you bought a new TV recently, or if you're in the market for a new TV right now, it's hard not to be overwhelmed with all the terminology coming at you, like 4K, UHD, or wide color gamut. What you should know, though, is that almost all new TVs today are classified as ultra high definition, or UHD for short. For a TV to be properly classified as UHD premium, it needs to meet a certain set of requirements, two of which are a minimum of 4K resolution and high dynamic range color output. So while sales of new UHD TVs are certainly on the rise, many of you may have noticed that the content landscape that take advantage of these new displays is somewhat limited. And that's a bit problematic, because gamers expect high fidelity visual experiences that also take full advantage of new console hardware. And that's where we as content creators step in. Now, our presentation today isn't so much focused on achieving 4K resolution, but rather addressing that 4K adds to a growing list of display resolutions that developers need to consider, and what other visual adjustments they may have to make. And with that, I'm going to hand it over to Kevin.
All right. Thanks, Charles. So as Charles mentioned, my name's Kevin Cogger, and I'm a senior software engineer from the Xbox Advanced Technology Group at Microsoft. I've been working at Xbox for over 11 years now, starting with XNA Game Studio. And since then, my career has spanned Xbox 360, Xbox One, Windows gaming, and Xbox One X. So my job is fairly similar to what Charles does, in that I work with our partners to help accelerate their game and engine development on Windows and Xbox One. In particular, I work a lot with Unity, and I've been helping to add features and improve performance in both Unity games and the Unity engine. One feature that I've recently worked on is dynamic resolution, which is what I'm going to be talking about today. So basically, as long as we've had real-time rendered games, there's always been this battle between frame rate and resolution. A higher resolution gives you more pixels to work with, which means sharper graphics, more detail, but it also takes longer to render on the GPU because you just have that much more work. This means that a higher resolution can lead to longer frame times and a lower frame rate. So games have basically always had to balance between these two, finding a resolution that looks good while also allowing them to hit a frame rate that's smooth enough and acceptable for gameplay. Historically, console games have managed this by finding a resolution that works for them and locking to that, whereas PC games have allowed the player to make the decision. But either way, the trade-offs are the same. So complicating this is the fact that not all of your frames are actually equal. If you have a particularly intricate frame with maybe a lot of characters, particle effects, post-processing, that's going to take longer to render on your GPU than a relatively simple frame. This means that even if you pick a resolution that gives you a good frame rate for the majority of your game, you might still drop frames during the most intense moments when you probably need that smooth frame rate the most. So to avoid this, you typically have to lock to a lower resolution, one that you know will give you a good enough frame rate during the most intense scenes, even if that means you're leaving power unused the rest of the time. Now, with today's consoles that have multiple hardware variations, like the Xbox One X coming out, this actually gets even a little more complicated. If you shipped a game on the original Xbox One and you lock to a resolution that gives you a good frame rate on that device, then you later run that game on the Xbox One X, it's going to stay at that same resolution, and it's not going to take advantage of any of the extra power unless you go back and update your game. So the question you might be asking about this is there a better way to do this? Do we really need to optimize for our absolute worst case and run at that resolution all the time? Or might there be a way to change our resolution based on the power we have available to better take advantage of what we can do? Well, as you may have guessed, this is indeed possible, and this is called dynamic resolution. You might have heard about this feature already, as it shipped in a number of major games over the last few years. And what I've done, working with my counterparts at Unity, is to bring this to the Unity engine. So dynamic resolution allows your game to measure its performance in real time, and then update its resolution on the fly to take advantage of the power that it has available and help you to continue to hit a smooth frame rate, regardless of how complex the view on screen is. Now, I should point out that dynamic resolution only helps you when your game is GPU bound, meaning that your frame rate is bottlenecked on the amount of work happening on the GPU. In cases where you're CPU bound, meaning your frame rate is primarily limited by long-running scripts or physics or anything like that, in that case, the resolution isn't actually the issue, so dynamic resolution isn't the solution in that case. Something to be aware of. Also, I should point out that this feature is shipping initially for Xbox One XDK games, meaning games built on the Xbox Development Kit, which is available to registered developers, such as through the ID at Xbox program. If you're using the Xbox Live Creators program, which lets you build universal Windows platform games, then you won't have access to this feature right away, but do stay tuned on that. All right, so I'm going to switch to a demo, and we can see what this actually looks like. So what I have here is a modified version of Unity's Viking Village sample. I picked this because it has some relatively high polygon models and a variety of effects, which make it GPU bound. And this means it's a good candidate for dynamic resolution. Now you might notice that right now, dynamic resolution is off, and the frame rate is inconsistent. I can hit 60 during simpler views, but when I bring more geometry on screen, it drops down to 30. If I turn on dynamic resolution, the frame rate immediately improves. We're now hitting 60 almost all the time. Instead, if you look at the UI in the upper left, you can see the resolution is actually changing based on the complexity of the view. Go all the way up or drop back down to half. Now you might notice there are still a few frame hitches in here you might be seeing. That's just because this is using a relatively simple dynamic resolution algorithm that's not fully tuned for this content. There's some frame spikes that occur in this sample. In a real game, you'll be able to tune your algorithm for your particular content and your performance profile to help avoid issues like that. Something else you might be wondering about is why I'm only changing the resolution in the horizontal direction. And essentially, that just gives us a better visual result for this and for most games, and I'll talk more later about why that is. One other thing I would ask, though, is if you ignore the UI in the upper left and just watch the graphics on screen, see if you can tell when the resolution is changing. It's actually pretty hard to notice, especially when the camera's moving. And that's one of the nice things about dynamic resolution, is when it's done well, players may not even realize that it's happening. All right, so now that we've seen what that looks like, let's take a quick look at how it actually works. So inside the engine, when you create a render texture, you'll still specify whatever your target full-size resolution is. And Unity will allocate graphics memory large enough to hold that render texture. It'll create a graphics resource there, and then it'll start rendering to it. If you later change the resolution, Unity will create a new graphics resource for the smaller size, but it's going to put it in the same memory allocation. It's now overlapped on top of your original resource. Change the resolution again, and it makes another one. The benefit of this is that we can fit all of these into a single graphics memory allocation, only large enough for your full size, rather than creating a bunch of render textures all over your memory. The reason this works is that only one of these will ever be active within a particular frame, so there's no conflict between them. You're only using one of them at a time. Now, when you change resolution, all Unity really has to do is swap a few pointers to ensure that the correct resource is active. In addition to that, Unity will also adjust the viewport for you to ensure that you're rendering with the correct size and aspect ratio. And it will also handle scaling back up to the full size afterwards. Now, UI overlays are always rendered at full resolution after the rest of your scene has been scaled back up. And that's just because UI is something that tends to look its best when it's rendered at full resolution. Because it has a lot of static objects and hard edges, if you change the resolution of your UI, that's going to be more noticeable, probably won't look very good, so we just take care of that for you. Now, I should point out all of this stuff is happening inside the engine. Unity is basically handling these details for you. In your rendering, you continue to see a regular full-sized render texture. You continue to see your regular aspect ratio. So all of these things Unity is taking care of. Now, at this point, you might be wondering, if I implement dynamic resolution in my game, and then I bring it to Xbox One X, is it automatically going to go all the way up to 4K? And the answer is not quite. So as we saw in that previous diagram, when you create a render texture with dynamic resolution, Unity still allocates the full-size memory for it. So on Xbox One X, your full size might be 4K. There's enough memory for it, and it's capable of 4K output. So you can do that if you want. On the original Xbox One, there's less memory, and it's not capable of 4K output. So you probably don't want to allocate a full-size 4K render texture. It would be wasteful. So essentially, you do want to specify your target resolution separately per hardware type, which fortunately is pretty easy. Unity has separate resolution settings for Xbox One, Xbox One S, and Xbox One X. So you can choose whichever one you want for each platform, and with dynamic resolution, it'll continue to scale against whatever your target maximum is. Now, something else that dynamic resolution gets you here is if you've chosen not to target 4K on Xbox One X. And you might do this because your art style or the resolution of your assets doesn't really matter with 4K, or maybe you just really want to focus on frame rate over resolution. If you do that, you can choose to target 1080p on all three of the hardware configurations, and you'll actually see a big benefit from dynamic resolution. If you run that game on the original Xbox One, you might find that the resolution has to scale down sometimes, just based on the complexity of the scene and the power. But that same game, without any other changes running on Xbox One X, will probably hit the full 1080p all the time, simply because it has that much more power, and dynamic resolution will automatically take advantage of the power available. So once you've implemented dynamic resolution, you don't need to do anything else to get that benefit. All right, so now that we've seen what this actually is, let's talk about how you can add it to your game. It's basically 3 steps. So first of all, you need to identify the render textures that you want to opt in to use with dynamic resolution, and enable them with this new property, Use Dynamic Scale. Now, this is already turned on for all the render textures that are built into Unity's render pipeline. So that means if you're doing something simple, like you just have a camera looking at your scene, outputting that to the screen, you don't need to worry about this for that. That's taken care of. Also, the post-processing stack and the Scriptable render pipeline repo will also have this set in all the right places once the feature ships. Right now, those repos are not updated because the feature hasn't shipped. This wouldn't work. But once it has, that will be there. If you have any custom render targets, then you do need to set this yourself. So that's if you've written your own post-processing effect, if you have your own scripted render pipeline, anything like that, then you'll need to make sure you turn this on for the right render textures. Now, you don't necessarily want to put this on every single render texture. In particular, it tends to look best for those that are rendered from the camera's point of view. So that's something like a G-buffer or maybe a full screen effect, but not something like a shadow map. And the reason is that with a shadow map, you're rendering it from a different perspective, and then you're projecting it back onto your main view. and if you change its resolution, you're likely to see artifacts in that process. Now, if you have a render texture and you're not sure what category it falls into, then you can always just try it out and see how it looks. Ultimately, the real test here is whether you're happy with the visual result that you get. All right, so once you've identified what render textures you want to use, the next step is to determine the actual resolution for the next frame. So this is the most complex part of your implementation because you do have to write an algorithm that, for your game's particular scenario, will look at your performance and decide what resolution you want to run at. So to help with that, you can use this class, Frame Timing Manager. This lets you get an array of frame timing objects which essentially provide performance information over the last several frames that you can use to figure out the best resolution. On some platforms, you will have access to some extended frame timing information. This gives you platform-specific details based on what that platform's hardware or APIs provide. So that might be additional timestamps or measurements or anything like that. And if you really want to optimize for a particular platform, then that's something to explore. So let's take a look inside one of these frame timing objects. So first of all, you get the CPU and GPU frame time in milliseconds. The CPU frame time essentially measures from one present to the next, and that includes time that the CPU may have been idle. The GPU frame time measures only the time the GPU was actually busy doing work. The next two values are timestamps. CPU time present called tells you when your CPU finished its work and called present to hand the frame off to the GPU. CPU time frame complete actually tells you when the GPU finished its rendering as measured against the CPU clock. The last values just tell you the dynamic resolution height and width scale for that frame, as well as the VSync interval. So something very simple you might do with this information to get started is to look at the GPU frame time and see if it's within your frame budget. If it's too high, then you may need to lower your resolution. Now, when you do find that you need to lower the resolution, you want to do that as quickly as possible, because otherwise your frames are going to run long and you're going to start dropping frames. But once you come back within your frame budget, you want to raise the resolution more slowly. The reason is that if you don't, when you're anywhere near kind of a performance borderline, you might start jumping back and forth quickly between different resolutions. And to see why you don't want to do that, I will jump back to the demo. So as you may have noticed on here, when I move to a more complex view, my resolution drops immediately. But when I move to a simpler view, it rises more slowly. It actually requires that we stay within our frame budget for a full second before it'll rise by one step. If I turn that feature off and I move sort of towards the borderline here, you'll see that it's rapidly jumping between resolutions. And if you look especially on the grass, you can kind of see a pulsing or a shimmering effect there from that. And that's distracting, it looks bad. Players might start to suspect that you're doing something funny there. So basically, that's why I would recommend avoiding that. So something else that you can do is to feed game-specific information into your algorithm to help anticipate changes in frame time. So for example, if you're about to generate an explosion, you might know that this is going to cause a particle effect, which causes more work on the GPU and increases your GPU frame time. In that case, you could lower your resolution in advance to help avoid dropping any frames. Also, as I'd mentioned originally, if you find that you're CPU bound, then you don't want to change the resolution because that's not actually your bottleneck and it's not going to help your frame time. So let's take a look at how you can tell whether or not you're CPU bound. So here we have a timeline representing the work that the CPU and the GPU are doing for a particular frame. At the beginning, the CPU is processing frame n, which means it's running your scripts, handling physics, and eventually sending draw commands to the GPU. Meanwhile, the GPU is finishing up the previous frame, and then it starts rendering frame n once it's done with that. This is where the CPU time present called timestamp from the frame timing object is. This shows when the CPU finished and handed it off to the GPU. this is where the CPU time frame complete timestamp occurs. This is where the GPU is actually finished rendering the frame. Because these are both measured on the CPU clock, you can calculate the latency between them. In this case, we see that the latency is relatively long. When the CPU finished, the GPU still had quite a bit of work to do for that frame. This helps suggest that we're likely GPU bound, that most of our work is happening on the GPU, so that's the limiter for our frame rate. In this case, we're CPU bound. Most of the work is happening on the CPU. The GPU actually had to go idle and wait until it had received enough draw commands from the CPU to begin rendering. The latency in this case is a lot shorter, and this is an indication that we're likely CPU bound. So here's how that might look in code. First of all, we grab both of those timestamps off of the frame timing object. Next, we calculate the latency in milliseconds by finding the difference, dividing by the CPU timer frequency, which you can always get off the frame timing, and then multiplying by 1,000. Then we divide that by the GPU frame time to get a measurement of latency in GPU frames. Finally, we apply a heuristic. We see if that latency in frames is less than a threshold, which I've defined as 0.5, and if it is, then we believe that we're CPU bound. Now, this is a heuristic-based approach, so it's not 100% guaranteed to always give you absolutely perfect results, but this is something that through experimentation my team has found generally gives you a good answer. So in this case, if you do find that you're CPU bound, then you want to avoid changing the resolution because it's not going to help your performance for that particular frame. All right, so now we know which render textures we want to resize. We know what resolution we're targeting. Finally, you just need to actually go and change the resolution. Now you do that with this call, Scalable Buffer Manager.resize buffers. This will resize all of your render textures that are enabled for dynamic resolution. Now it takes float scale values, and the reason we take floats there and not an actual pixel resolution values is because it will resize all render textures that are enabled for dynamic resolution. They may be in different sizes, and you want to resize all of them proportionally. So the float values allow you to do that. Essentially 1.0 means full size, and anything less than that is that much smaller. What I've found in my tests, in my sample, is that going down to about half resolution tends to look good, and increments of about 0.1 seem to be a good amount. Do keep in mind that because this modifies your render textures, you want to call it before you've rendered anything. Now normally, Unity handles all that for you. Your script will run before it renders, so you don't need to do anything special. But if you've done anything particularly interesting in your scripts where you might be manually kicking off some render while your scripts are running, you just want to make sure that you've called this first. Now because this modifies all render textures, you only need to call it once per frame. And of course that means your algorithm calculating the resolution also only needs to run once per frame. So I would recommend that you place these maybe in some sort of global dynamic resolution manager object that can live in your scene and run that script. So that's just a matter of creating a new game object, adding a script to it, script component which will hold your algorithm, and then just implementing it in the update method. Now you want to make sure to put that in update and not fixed update or late update, just to ensure that it runs exactly one time per frame and at the right time. Now I've mentioned that once you do this, Unity handles most of the other details of the actual resizing, of ensuring that your aspect ratio and everything is fixed up. There are a couple places where you'll need to pay a little bit more attention if you're using dynamic resolution. So in post-processing, if you're using any effects that use history buffers, like temporal anti-aliasing, you need to reset those buffers when you change the resolution. The reason is those buffers hold data from previous frames, which is going to be in the previous resolution. And if you try to run those against your current resolution in a shader, you're likely going to get corrupted results. So you just want to make sure that you reset those, which you can do in the post-processing stack with reset temporal effects. If you've written your own post-processing effects, then make sure that you set use dynamic scale to true for any render textures where it's appropriate. And if you have any effects that you found don't work well with dynamic resolution, this might mean that you just haven't had time to use dynamic scale and fix any bugs, or maybe you're doing something that really is dependent on a particular resolution size. It is possible to disable dynamic resolution for an effect using this attribute, image effect after scale. And what this does is this will cause your effect to run after all the other effects and after your render textures have been scaled back up to full size. Now this does change the order your effects run in, so it might give you different visual results. And it also means that effect doesn't get any performance benefit from dynamic resolution. So this is something that I would recommend avoiding if you can, but if you really need it, it's there for you. Now, if you've been looking at the scriptable render pipeline, this also means that you're working with graphics at a bit of a lower level. And you may find there are some cases where you need to account for the real size of your render textures, including the scaling. So you can calculate this using Scalable Buffer Manager, that width scale factor and height scale factor, which give you back those float values that you passed in when you last called resize buffers. Also, for convenience, the camera class provides scaled pixel width and scaled pixel height, which is the real adjusted size of the current render texture that it's rendering to. As with everything else, of course, make sure you set use dynamic scale for the right render textures. And as I mentioned earlier, the Scriptable render pipeline repo will be updated with these changes once the feature ships. So finally, just a few tips to help your dynamic resolution look as good as it can. I'd recommend that you only change the resolution when the camera is moving if you can, or when there's other heavy motion in the scene. As you might have seen in the demo, that motion helps to hide the resolution changes. As we also saw, you want to avoid bouncing rapidly between sizes, because that can be distracting and visible. And finally, the reason that I was only scaling in the horizontal plane is basically for most games that tends to give you better looking results that are harder to notice as well. Most games tend to have most of their motion in the horizontal direction, whether that's camera rotation or side scrolling or things like that. And that horizontal motion helps to hide horizontal resolution changes better. If your game is different, if you have a lot of vertical scrolling, for example, then you might want to do something different there. And that's something you can always experiment with. And yeah, done well, a lot of this can make it hard for players to even notice that the resolution is changing. So to sum up this section, before I hand it back to Charles, dynamic resolution helps you to maintain smooth frame rates with the best resolution possible at any given moment. It makes your games more resilient to hardware variations and better able to take advantage of the power they have available. Implementing it is largely a matter of marking the right render textures, calculating the new resolution for each frame, and then calling resize buffers. This will be available in Unity 2017.3, first for Xbox One XDK games, and there will be a sample on the Unity forums around the time this ships, and I would definitely recommend taking a look at that. It should show how to call these APIs in a lot more detail, as well as have an example dynamic resolution algorithm that you can use to get started. And yeah, with that, I will hand this back to Charles.
All right, thanks a lot, Kevin. Not long ago, I mentioned that together with the Microsoft Xbox team, we've been able to bring really cool tech like dynamic resolution to Xbox developers using Unity. As part of our mission to democratize game development, we pursued the possibility of taking the awesome work that Microsoft did here and porting it to other Unity platforms. We're proud to announce that in a future Unity release, dynamic resolution will also be coming to PlayStation 4, Nintendo Switch, PC, and mobile platforms. Not only will your game be able to take advantage of dynamic resolution across multiple platforms, but everything that you learned here today will be completely relevant and 100% applicable. So now we'll be talking about another important display technology, high dynamic range, or HDR as it's commonly abbreviated. Now what I found from talking to a lot of developers is how often HDR is misunderstood. And as a result of that, how developers will actually go out of their way to intentionally avoid HDR, which to be honest is a bit unfortunate. because HDR, when done correctly, is a great and compelling way to showcase your game title. I'll start with spending just a bit of time reviewing the foundations of HDR, then how your game can start taking advantage of it right now. So first, why HDR? Well, as it turns out, HDR is rapidly becoming a key game changer in today's class of TVs. Multiple studies have shown that HDR resonates very well with consumers, both gamers and non-gamers alike. Browse any tech blog today, and you'll find that the press has almost universally praised HDR support. And among gamers, its popularity has been driven by consoles like the PlayStation 4 and Xbox One S released last year. On Xbox One S and the Xbox One X, HDR10 is the supported media standard to output HDR content to the target display device. To summarize the HDR10 media profile, the standard uses the Rec 2020 color space, which we'll go into in a bit. Combined with a larger color space, the format also utilizes the ST2084 electro-optical transfer function, which controls the output luminance. All of this data is then encoded in 10 bits per channel, up from 8 bits we typically see today in non-HDR content. In general, these specifications are indeed very large jumps from the previously accepted standards. Take, for example, this diagram, which is used to represent the color gamut visible to human eyes. As a reference point, the dot here labeled D65 is used to represent white. Today's HD TVs follow the Rec 709 color space, which, as it turns out, covers only 35.9% of the visible color spectrum. HDR TVs, on the other hand, follow the newer Rec 2020, which covers over twice that surface area, reaching 75.8% coverage of the visible color spectrum. Now, it's incredibly important to note that the colors between Rec 709 and Rec 2020 are not actually visible on the screen, because the projector used in this room is not HDR capable. Something I've always found really interesting was that up until recently, it actually wasn't possible to accurately display that distinctive red color that you find in Ferrari cars. This is due to the limited range of the Rec 709 color space. With the advent of HDR, modern racing games were finally able to accurately portray that specific shade of red in Ferrari cars. Other notable examples include the orange color that you find in traffic cones. Personally, after learning this, I've come to never look at traffic cones the same way ever again. It's also important to note that, as of today, there are no consumer TVs capable of displaying colors beyond the Rec 2020 color space. In fact, there's actually no consumer TVs at all capable of even displaying all of the colors defined in the Rec 2020 specification. Color space, though, is only part of the overall picture. In 1999, a researcher named Peter Barton developed a contrast sensitivity model based on physics and optics. And it happened to align very well with several decades of research done in this area. Now, one outcome from this research was the creation of something called the Barton ramp, shown here, which mapped our perceptual responsiveness to changes in luminance. Today, the Barton ramp is largely regarded as the ideal model for luminance output in television units. We measure luminance in a special unit called nits, which is also defined as candelas over square meters. For luminance, regular HD TVs today use BT 1886, which, as you can see, is somewhat limited in its range and function and has a fixed contrast step. Modern HDR TVs, on the other hand, use ST2084, which aligns much more closely with the Barton ramp and has a wider range of luminance in terms of nits. And of course, all of this is encoded in 10 bits, allowing for significantly more colors than ever before. The majority of regular HD TVs peak at around 100 nits, with most HDR TVs peaking at around 1,000 nits. This increased brightness levels allows HDR TVs to better simulate natural lighting conditions. So before we can see how all of this is put together, let's quickly review the non-HDR rendering pipeline that most games today use. Let's begin with your game scene in the Unity editor. At this point, your scene may or may not already be using HDR source materials. And in this case, even though we're outputting to a standard HD TV, the HDR source materials could still be used for any post-processing effects that you have. And because the final output of this is a non-HDR image, we need to tone map that into the appropriate standard dynamic color range. We store all of this information in an 8-bit proxy render target. Next, after your game's UI layer is composited, the final frame is presented to the target display device. Now, if you play a game on Xbox, PlayStation, or Windows 10, these platforms allow you to record game clips that you can share with your friends, or maybe upload them to YouTube or Twitch. On Xbox, this is called Game DVR. So what happens is that if you frame present, the Xbox OS will automatically retrieve the frame buffer from the GPU to construct that Game DVR clip. In total, this process uses one swap chain and a single 8-bit back buffer. The HDR rendering pipeline doesn't look terribly different, but it does have a few key differences. First, instead of tone mapping to SDR, we need to adjust the tone mapping step that's more appropriate for HDR. The frame data is now stored in an FP16 proxy render target, up from 8 bits. Using FP16 gives us a good balance of performance and storage to store lighting computations. The final frame is then stored in a 10-bit back buffer that we present to output display device, as required by the HDR10 media protocol. So at this point, you might think that we're done, but we're not quite there yet. Well, as it turns out, we still need to present an SDR frame for Game DVR. And this makes sense, because we want players who don't have the newer Xbox or an HDR TV to be able to watch your game clips. So while our HDR10 image is complete, we'll also need to construct an SDR frame. So to do this, we'll need one more swap chain and another 8-bit back buffer to store the additional frame data. Internally in the Unity engine, we simply apply another shader after the UI is composited that remaps the colors to SDR. So in the final step, we now have both an HDR and an SDR frame, and we present them at the same time to the output display device. So now that everyone here is an HDR rendering expert, let's get down to actually adding HDR to your Unity game itself. What you're going to need first is the right dev kit. For Xbox, that's either the Xbox One S or the new Xbox One X. And of course, you're going to need an HDR TV. Now, from our experience, we found that quality among different sets does vary drastically. And we've seen really cheap entry-level HDR TVs claiming to offer true HDR support, only to find that they sometimes don't support the necessary color depths or the right color gamuts needed for true HDR. Artings.com is a great website that you can check out. It has comprehensive listings of HDR TVs, allowing you to compare luminance, color depth, and color gamut, among many other specifications. If instead of a TV, you wanted to use a monitor instead, your choices are a bit more limited, with only a small handful of HDR monitors available on the market right now. However, more HDR monitors are expected to roll out sometime next year. Color calibration is another step that you may want to consider as well, since every manufacturer is almost certainly going to have different settings on their HDR TVs. The X-Ray Colorimeter is one such tool that's been well received, and it runs a little under $300. With your equipment set up and your XDK installed, you'll want to make sure that Allow HDR is set on the console. You can either do this through the dev kit itself, or use the Xbox One Manager tool included in the XDK. All of the other settings shown here, including color depth and color space, don't really matter in the context of our development right now, and can be safely ignored. On the Unity side, you're going to need to select Allow HDR on the appropriate cameras, This setting tells Unity to store your frame data in the higher precision FP16 format instead of 8 bits. Next, you'll need to double check that Use HDR is checked in the graphic settings. This allows you to toggle whether you want to use the high precision format for the proxy render target per graphics tier. It's a bit more relevant in the context of PC, and for Xbox, it is on by default. All you need to really do here is just make sure it's already checked. In the future, you'll be able to select what high precision format you want to use. For now, you're limited to FP16, but the options we'll add later on will have different performance characteristics for quality trade-offs. The last setting you need to turn on is Use Display in HDR mode. When this is enabled in the player settings, Unity will use the HDR rendering pipeline instead of the SDR rendering pipeline. Also with this setting, your executable will send a signal to the TV to enable HDR mode on startup. So in total, there's just a few settings you need to turn on within Unity to fully enable HDR. As for HDR content creation, Unity actually makes it pretty easy by already supporting industry standard HDR formats like OpenEXR. The texture importer will also automatically choose the right HDR format for the output texture when you import them. Your shaders can also take advantage of something called the HDR color picker built right into the Unity editor. It looks incredibly similar to the regular color picker with the addition of a brightness selector and the ability to look at the tone map preview. In most cases, however, you'll find that only having the skybox and a small handful of other textures authored in HDR is necessary for your game to be visually compelling. And if you want to take a look at how some of these things work, you can actually check out the Viking Village sample on the Unity Asset Store, which already has an HDR skybox and a few other HDR source materials that you can reference. Also available on the Asset Store is the post-processing stack, which includes the color grading image effect. If you have HDR assets, it's a pretty handy effect to extract details or adjust the final color and luminance. And if you're looking to avoid adjusting assets altogether, one technique that you could do is to write a shader that remaps your SDR frame into HDR. Effectively, you can think of it as an inverse tone mapper. So for instance, let's take a look at the SDR rendering pipeline once again. If you wanted to go with the inverse tone mapper approach, you would simply add an HDR shader right after the UI is composited. So while the benefit of this approach is that you don't need to update your assets, the results will ultimately depend on the quality of your HDR shader. And we all know that it can certainly be hard to maintain artistic intent in code. For example, because we're adding the shader after the UI is composited, you may find that you have to dim your UI a bit for a more consistent look. And at least one game I can think of has shipped doing this, and the final result did look quite fantastic. Of course, your mileage will vary. And lastly, as we described earlier, your HDR-enabled game is almost certainly going to look different across different TVs. So for that reason, you may want to consider adding a color calibration option in your game settings, allowing your players to fine-tune the color to their liking. And with that, you're on the way to shipping an HDR game using Unity. Let's briefly recap with a few key takeaways. First, HDR TVs have shown a lot of promise and expect to reach the homes of millions of consumers. Next, even if you're creating a non-PBR game, your title can still benefit from HDR, as you have a much larger color space to take advantage of. And as I've shown today, Unity makes it incredibly easy to add HDR to your game. In fact, you don't even need to worry about branching code paths. When your game is running on the base Xbox One model, or if a non-HDR TV is connected, Unity will automatically fall back to the SDR rendering pipeline. Your biggest challenge, however, is going to be making your game look good across different devices. The features that we talked about today give developers more options than ever to build the game of their dreams without compromising frame rate, resolution, or colors. To summarize once again, dynamic resolution is coming first to Xbox in 2017.3 and arriving on other platforms soon after. HDR is available right now for both PlayStation 4 and Xbox One. And that concludes our presentation today. It's been great to work with Team Xbox to put these really cool features in the hands of developers, and we can't wait to see what you guys come up with. Thank you so much for watching, and at this time, we're happy to answer questions or take feedback.
Unity support for HDR on the Windows desktop. Is it going to come? Is it going to be available if I want to hook up my HDR TV? Yeah, if you could say anything about that.
Yeah, so the question was, is HDR coming to PC? And the answer to that is we are looking at it and something we are exploring very deeply.
Hi, so if you're targeting mobile or in particular just iPads for, say, an AR experience, is there still an advantage in using an HDR workflow, or does the end device, that in this case an iPad, that's going to defeat the purpose? It's not going to show the HDR? I'm sort of confused there.
So the question was, does it make sense to use HDR for some platforms like an iPhone or some AR, VR kits? The answer to that is a little bit more complicated, and it's very device dependent. I believe there's actually just an AR or VR kit announced not too long ago, and it was the first of its kind to offer HDR support. It's something we're looking into right now, but as soon as we sort of figure it out, it's definitely something we want to look into. When HDR support is fully supported on these platforms, on the actual hardware, HDR will make a difference.
Hi, a couple resolution questions. So first, you mentioned with techniques like temporal AA, when you're scaling things, you could get those scaling factors or whatever to sample in the shader for the previous frame. What if you had a technique that was valid for, right? Obviously, AA, it wouldn't be, but you might have some other effect that you're trying to achieve. Could you get the values so that you could do a proper texture lookup to do that?
Yeah, so you're asking about if you had an effect where you've changed your resolution, but you still want to look at the history buffer,
Right.
the old resolution. Yeah, it should be entirely possible to do that. Basically, if you don't call reset temporal effects, then they won't get reset. The history buffer will still be there. So as long as your shader knows about that, then you should be able to do the right thing with it.
Okay, cool. And the other one, kind of related resolution that you guys didn't talk about that everyone seems to be doing is things like checkerboard rendering, so that you can also manage or get the perceived kind of pixel count.
Yeah.
Are there plans to go in that direction as well?
So I don't know, as far as Unity is concerned, I know it's not in there now. I don't know if that's something you guys have thought about.
I believe you're asking about the future of checkerboard rendering.
Basically, yeah.
Right, so checkerboard rendering is actually available for PlayStation 4 right now, and it's definitely something we're looking to bring to Xbox One very soon.
Okay, cool, thanks.
Hello, for dynamic resolution scaling, what kind of impact does that have on the CPU? So if you're having an issue with your GPU, but your CPU is like already pretty pumped, is there much of an impact on CPU?
Yeah, so I don't actually have numbers on that. Was hoping to get some measurements. We haven't been able to do that yet. My understanding is it should be pretty minimal. There's not a lot that's happening on the CPU for this.
For the dynamic resolution, for the Windows support, how do you anticipate that's going to be affected for like head-mounted displays, like VR headsets?
I can answer.
Sure.
So the question was, how does dynamic resolution might sort of work with AR or VR headsets? That's actually an interesting question, because on VR and mixed reality, really, and other Rs, we're actually looking into something called adaptive rendering, which is very similar to dynamic resolution. I don't know how far along we are with that, but it's definitely something we're exploring. So stay tuned for more XR-related resolution announcements.
Thank you.
I guess I can kind of comment on that.
Yeah,
So,
yeah, that's great.
Yeah, the reason it's different across different platforms because not all platforms have explicit APIs, or at least the different implementations don't. So you can't swap the memory out under the descriptor, right? So that's why I was kind of
Yeah, that's something I forgot to mention on there is
Yeah.
that it is platform dependent on how that's actually
Yeah.
implemented.
So yeah, so if you're on DX11 OpenGL, you can't unless something secret is being worked on, which I'd be very surprised by. You can't do that kind of technique. So you have to use viewport changes, which is not like this is the ideal implementation. It's just not on all platforms or all APIs. Sorry.
Yeah. The question was, when is 2017.3 arriving? It will arrive after 2017.2. We are aggressively aiming for 2017, so before 2018.1. Any other questions? So we'll actually be in Ask the Experts right after this. So if you guys have any follow-up questions, feel free to drop them by. Thank you so much.
Yeah, thanks.